All right, so this is our second lecture in our series of 3 on reverse engineering machine code. In this segment, we're going to be talking about the various kinds of breakpoints you'll encounter, C++ reverse engineering, symbols and name mangling, and we'll conclude with a few Windows internals that are important to understand. So first, on the breakpoints, there's 3 main types. There's software breakpoints, which we've talked a little bit about in previous lectures. This is the interrupts, int3 interrupt that we discussed. There's also memory breakpoints, and this is implemented through a mechanism called page guarding, and hardware breakpoints, which is implemented in the actual CPU. So software breakpoints, this is just an interrupt. On Intel, it's the int3 instruction. And when this is encountered in software, it generates a debug event that the debugger catches in process, just called exception debug event. So pretty simple. To set, like if you were to either manually write your own debugger or doing this by hand, wanted to set or clear a breakpoint, this is the basic process that you would go through, and this is what debuggers that you'll use, like OllyDebug, WinDebug, do when you actually say, "Hey, I want to break at this particular address." What the debugger is going to do is it's going to record that byte value at the original byte value at that address. It will modify that to be the CC byte, which is the opcode for int3, and then when you run the program, when that CC byte is encountered, the debug event will be generated. The debugger stops. You're able to do whatever you want within the debugger, inspecting the state of the program, etc. And then to clear the breakpoint, it's just a matter of restoring that original byte and resuming execution. So fairly straightforward process for this. One of the things you'll notice, though, about when I described how software breakpoints work is that these software interrupts are changing memory values. So this is detectable, which this comes into play if you're reverse engineering a program that happens to have some anti-debug mechanisms, or in cases where integrity checks may be performed. If an integrity check is performed over the memory where you set your breakpoint, that's going to throw off that checksum or hash, depending on what calculation is being performed. With memory breakpoints, here we're using, in the Windows API, there's a function called virtual protect. And what this is essentially doing is this is setting a few page protections, depending on whether you specify you want to break on read or write or execute. Essentially, when that page is read from or written to, then this is going to generate this status guard page violation exception. And again, this is something that the debugger will handle and let you then take whatever action you want once that's encountered. So this is good if you're wanting to let the program run until some area of memory is either written or read from. This can also help you narrow down, from a reverse engineering standpoint, an interesting section of code. If you know the code that you were interested in touches a particular region of memory, but you're not sure where that code is, maybe it's encrypted statically, and so you're wanting to wait until that code is decrypted. Well, this is a memory breakpoint would be of great use there, because you could set a read breakpoint, for example, or a write breakpoint. And when that action is taken, the debugger will stop, and then you'll be able to figure out what section of code actually touched that page in memory. And the third type of breakpoint is hardware breakpoints. These are implemented in the processor. These are not interrupt instructions. And so there's actually special hardware dedicated to these breakpoints. So they're quite useful, but at the same time, because this is something that's implemented in the hardware, there's also a finite number of these. With software breakpoints, you can set as many breakpoints as you'd like. With hardware breakpoints, here on the x86, you're limited to 4. And that's what's going to be contained in DR0 through the DR3 registers. These will hold the actual addresses that you're setting the breakpoints for. So you can have up to 4. And then the DR6 and 7 register, these set properties and options associated with your 4 hardware breakpoints. And so what I mean by that is things like, should it break on read access, should it break on write access, should it break on execution. These bits, and that's what these numbers are that you see here at the bottom of the screen, this corresponds to, within that 32-bit register, those are the bits that correspond to the different trigger options. And so if you want more detail on these, I'd recommend consulting the Intel manual for more extensive information. But these are quite useful when you're debugging the program, especially if you don't want to actually modify the code. And then this is a screenshot from OllyDebug, just kind of illustrating the type of control you have. You can see the 4 hardware slots corresponding to the 4 breakpoints, the data size, so are you concerned with a byte, word, or double word, for example, and then the type of break that you want, whether it's on execution, write, or read. So, all right, so now we're going to move on to talk more about C++ reverse engineering. Many people consider C++ in general a very difficult language to reverse engineer, and part of this is just because the language itself is very powerful in what it allows you to do, and some of that power, such as what you get from how polymorphism is implemented using virtual functions, that leads to more indirect calls, indirect jumps, and whatnot, which from a reverse engineering standpoint can get tricky because you don't, like in C, if a function is being called, it's going to say call, and then there'll be the address of whatever function you're calling. If it's a virtual function in C++, you're going to see an indirect call where it's calling an offset from a register. And so if you're just going through the program statically, it may not be obvious, right off the bat, well, what function is this actually going to call? And that may force you to do more dynamic analysis with the debugger. So what we'll do here is to try to demystify some of that and walk through a few examples so you have a better understanding, like how do vtables work and things like the this pointer, for example. How is that represented at the assembly level? To start with, this is a very basic C++ class, just to kind of refresh your memory if you haven't done much C++ programming. Here we have a class named foo that is inheriting from a class named bar. Foo has both public and private members. You have the constructor and a destructor, as well as a public function called doFoo, and then you have your private variables and as well as a private function. So in this class, we don't have any virtual functions. This is just a very vanilla C++ class. Whereas in this example, we do have a virtual function. So virtual functions provide polymorphism in C++. So that lets you, if you have a parent class A, as in this example, we have a subclass B that's inheriting from class A. You can see that here, because the function called func in class A is marked as virtual, that means that anybody who inherits from A, they can override it and do whatever alternative functionality. And so that's exactly what you see here with class B. It's also defined a function called func, and it's printing B. So if you move further down below, you can see a new instance of B that's being created, and it's func routine being called. So what this is actually going to do is this is going to print B. It won't print A because in this case we have a specific instance of B that's being created. So the way this actually gets implemented at the assembly level is through what's called a virtual method table, or vtable. And all a vtable is, it's just simply an array of pointers to functions of an object. So every C++ object is going to have a vtable, assuming that it is using virtual functions, and a v pointer that's just pointing to that vtable. And so you have a little differences between what compilers are used, but on Microsoft, this is going to be the first member of that object in memory is going to be the v pointer, and that's going to be a pointer to the vtable. In Unix, this is going to appear after all of your user-declared members. So just to give a very simple example of what does an indirect call look like at the assembly level. The first line here is moving a vtable pointer into EAX. Okay, so EDI in this case is your this pointer. So that's pointing to the object, and as noted above, the first member of that object is going to be the v pointer. And so in this case, by having the brackets around the EDI, this is getting the value of the v pointer, moving it into, or of the vtable, moving that into EAX. ECX is getting assigned to this pointer, and that's another convention that you'll see where the this pointer is typically passed to functions through the ECX register. Then we have the call statement, and here the call is, it's calling a pointer, and so this is the D word, the next D word after EAX. So this is essentially, so EAX, again, is the vtable pointer. It's calling the function that's at EX plus 4, which is going to be a method from the vtable. All right, so the next few slides we're going to walk through a little bit more detailed example where we have multiple classes and some more code, just so you can kind of see how the assembly gets generated from that when you have vtables in use. So here are the first two classes, B1 and B2. Both of these have virtual functions, F1 and F2 respectively. They also both have an integer member or field. And so if we look at B2, so this code is creating a new instance of B2. And the way this will be laid out in memory is that for B2, at the beginning, we're going to have, of course, this is the v pointer to the vtable of B2. After the next D word, that's going to contain the integer that you saw, the int in B2. And then the vtable itself of B2, there's just the one virtual function, so this is going to have a pointer to B2's instance of, or implementation of F2. Now we have a class D, and D is inheriting from both B1 and B2. In D, we see that it's overriding B2's instance of F2 by having its own F2 function. And we also have an int in D variable as well. So if we were to drill down in to see how D is going to be laid out, now again, D had multiple inheritance, so it's inheriting from both B1 and B2. So it actually has two pointers, two V pointers. The first, since it's going to have the data that inherited from B1, so a pointer to B1's vtable, as well as the value of the int in B1. Then it also, after that, is going to have a pointer to the vtable D for B2, the int in B2 at the next D word, and then last, it actually will have the int in D variable. Then you have the other two vtables. Now for D, if we look at the vtable for D for B1, we see that this is actually going to be pointing to B1's instance or implementation of F1. And that's just because F1 is not overridden by D. But the vtable of D for B2, however, this is going to point to D's version of F2. And that's because it's actually overriding B2's version of F2. So to drill down even further, now we have our three classes that we walked through. You can see some implementation for the different functions, F1, F2, etc. And then on the right here, we have a main routine where we're creating an instance of the three types of objects and then calling the functions and setting the integer values. And so what you're seeing down here below at the bottom of the screen, this is a clip from Ollie Debug, and we've set, just to make it easier here initially, we set breakpoints actually on the main lines of assembly that correspond to this code. So if you look through the assembly, this actually looks fairly straightforward, just in terms of correspondence to the source code. But you will note that this isn't contiguous. So there are actually other instructions that are in between some of these lines, and we'll see those here in a bit. But to give you an idea of what's going on at the assembly level, you can see the calls to new. You can see the integer assignments with those move instructions, and then you can see the other calls that are made. And it may look a lot more confusing than some of the C code that you have looked at in Dissembler, just because here we have these calls to pointers and the register, and that gets to be a little bit more confusing if you don't know what's actually at those, or what values are in those registers. So next we'll drill down into the B1 constructor, and this is just to kind of illustrate the constructors in C++. These are going to be responsible for initializing the vtable for that object. So if you wanted to figure out, well, where is B1's vtable, you'd go to its constructor, and you'll see if you go halfway down at address 401.430, you can see pretty plainly there that that's where the vtable of B1 is being assigned to EAX in the data segment there. Well, you may wonder, well, what is EAX? If you go up 2 more instructions previous to that, we see this pointer being assigned to EBP-4, and then on the stack, and then EBP-4 is being moved into EAX. So this is in sync with what we talked about earlier, where the very first member of that object has the pointer to the object's vtable, and that's by having the brackets around EAX. That's essentially, think of it as dereferencing EAX, and so it's writing in that v pointer to its vtable. And if you were to look at the constructor for the other objects, you would see a similar code to this. So now you see all of the code. The red lines on the far left and highlighted in red, that's what you saw on the previous slide where we had set the breakpoints. So just and Ollie, they always highlight in red, so that's how you can tell. And in between, you can see all the extra logic, where it's assigning different values to the registers. So in this case, EBP-10 corresponds to B1, EBP-14 corresponds to the object B2, and EBP-18 corresponds to the object D. And so if you look through this code, and we're spending some time just to study it, you can kind of see the logical progression as it's getting a pointer to the object, then it sets, in the case where it's assigning either the 1, 2, or 3 value, it's setting that value as an offset from the beginning pointer of the object, so to this pointer. And then you can see where the calls are made. You can see how, like down towards the bottom, for example, the call dword pointer to ds EAX. And so if you trace up to see, well, what got assigned to EAX, you can see that this pointer for the D object was moved to EDX, and then we have pointer to EDX plus 8, which makes sense because when we went through previously how the D object was going to be laid out, this is the pointer to the B2's vtable. That's assigned to EAX, and then you have a call excuse me, a call to the the value at dx. So fairly straightforward once you kind of get the feel for how this is laid out, but it is a bit confusing. If we take out some of the compare statements that aren't as relevant to the source code here, this makes it a little bit even easier to follow. So I'll just leave this up for a second so you can take a look. All right. All right, so now we're going to move to talking about symbols. Symbols, as the name implies, this is just the names that you assign to your variables, your methods, classes, etc. When you build your program, these get compiled into the final binary. You may have seen, depending on what compilers you use, like Visual Studio, for example, there's options for compiling in debug information. Same with GCC, where there's various debug options. When you avail yourself of these, and then you disassemble the program, or you're viewing them in a debugger, it becomes a lot easier to read through the program because you see all the meaningful names, and so it's not as much of a mystery reversing and looking through code with symbols as it is one that's been completely stripped, and so all you see is just a call to some address, and it may not be obvious, well, what's actually at that address. And so most debuggers and disassemblers do have support for symbols, and so if the symbols are available, you can load those in. Microsoft also makes available on their website all the symbols for their Windows operating systems, and so you can download those, and if you're using IDA Pro, for example, it will load in all the symbols, and then you see meaningful names in the disassembly, and that can really speed up the process, the reverse engineering process, as you go through. So along with the symbols comes name mangling, and then name mangling, it's up to the compiler actually, in many cases, how this is done, but this is the reason for name mangling is to distinguish identifiers the same name in different namespaces. So if you think about different functions where you may have the same function name but different parameters, difference in return types, same with classes, the compiler needs to have a name for it that's uniquely identifies that routine, because it's not going to have the full long name that you would see in your source code in the binary. So in C, this is fairly standardized and not as useful, just simply because C doesn't support function overloading. And so here we have an example of a cdecl standard call and a fast call, and we have an f, g, and h function, each that take an integer option, and then you can see down below, this is what the mangled name looks like for those functions. In C++, name mangling is heavily used, and it's also mostly non-standardized. So down below, if we look at another similar example, here we have two functions called f, but one has a void, the other takes one integer parameter. You can see how the mangling here disambiguates between the two, v being for void, I being for an integer parameter. But this can also get quite ugly, as you'll see in this chart. So here's essentially the same or similar routine. These are the exact same functions here. So for a void h with two functions, or two parameters, sorry, int and a char, you can see this is what the compiler would produce for the name mangling. If you're interested in name mangling, there's a lot of resources online that will go into very great detail on exactly what each of these means, and it's actually not as complicated as it may look. But if you're unfamiliar, you look at that and you're like, what's that going to do? And but fortunately, most good debuggers as well as disassemblers are all going to take care of name demangling for you, and so you don't really have to worry about it too much. Really, where it comes into play is if you're writing some plugins or analysis tools, you may need to deal with demangling, but even then, in the plugin model for IDA as well as Ollie, there's API calls to do name demangling. So it's good to be familiar and understand they exist, and then if you just turn on demangling, so it's easy to, when you're reversing in code, to just see exactly what the function is and not worry about all the details of how it's mangled. All right, so the last bit that we'll talk about here are some of the basic Windows internals that govern the execution environment when the program's running. Where these really come into play, especially if you're ever writing your own debugger, understanding how process and thread information is stored, where it's stored, how exceptions are handled, but also just if you're just debugging a program in general, you want to get information about that program, or writing other tools to extract that state. These are all things that are important to know. So first we're going to talk about the PEB, which is the process environment block. The process environment block, it's, as far as where it's located, this is at this offset from the frag segment, hex 30. If you want to get more information on the specific details of the PEB structure, you can consult. There's a book called Windows Internals, or you can search online, and there's a lot more information about it there. But this is going to be information initialized by the kernel, or PE header, and it's going to have runtime information about the program. One of the things that becomes interesting from a reversing standpoint is to be aware of is that there's this being debugged part of the structure. And so if you have a debugger attached to the program, this is going to be set. Now, the reason why that's important to know is just because there's some programs, and I think I mentioned this earlier, that want to try to detect, hey, is anybody debugging it? And so that they'll actually consult the process environment block as one technique of determining whether a program is being debugged. This also contains information about loaded modules, so DLL files and the like, as well as things like command line arguments. The thread environment block, similar to the PEB, again, this is going to have information about a single thread. So you have the process environment block, and then it may have multiple threads, and then for each one of those threads, you're going to have one of these TEBs. This is located at offset 0 in the frame segment, and it's going to contain things like the process thread ID, pointer to its PEB for the process, as well as the current SEH frame. So SEH, that stands for Structure Exception Handling, and I'm actually going to be talking about that next in a couple slides. So both the main takeaway from the PEB and the TEB really is that these are the two resources. If you want to get information or query information about a process or running threads within a process, these are your go-to source for that. So you can inspect all of this information from within a debugger, but you can also do it programmatically. The other thing to note about threads is that there's also a thread context, and so this contains the state of execution for that thread. So all the registers, general purpose, memory segments, etc., instruction pointer. Each thread has a context, and so as the operating system is going through and context switching from one thread to the next, it's having to save, restore this context for each thread. And this is another thing that you can also get access to programmatically, or looking at in memory, you may see the thread context information stored. The other piece about Windows is it affects the runtime is how it handles exceptions. So there's three main types of exception handling. There's vectored, structured, and then the unhandled exception filter. The first one we'll talk about is vectored exception handling. This was a feature that started in Windows XP. It essentially has a chain of pointers to handlers that are stored on a heap as a linked list. So very simple structure. And when you have an exception that's triggered in the program, this is the chain that is traversed first. So this handling is gonna occur before frame-based handlers like SCH, which is what we'll talk about next. The key thing to note about vectored exception handling is that these can be triggered anywhere in the process. It's not there's not a particular region of code that you're guarding or that you've wrapped in try-catch like blocks, and so these aren't frame-based. This can be anywhere in the process, and that's the main difference to keep in mind. So with the structured exception handler, this too, it's a chain of pointers to handlers, except the SCH pointers, this chain is located on the stack, and it's also set up as a linked list. And so in your source code, if you've used try catch blocks or try except blocks, that's corresponding to structured exception handling. And so for those particular blocks of code that are guarded by the try catch, there's going to be an entry and there's a handler that corresponds to that. So as it's going through this chain, it's looking to see, hey, does this type of exception match what was triggered? Is there a handler for this? And so it will kind of iterate until it finds a handler that does accept it. And so that's exactly what we say here in the last bullet, where essentially this is going to be traversed just like the vectored is traversed. Now, if there's no handler to accept it, that's when you run into this unhandled exception filter. And this is sort of the last-ditch effort. If nobody else has handled the exception, the program is basically about to crash unless somebody does. And so the dialog boxes here, this is essentially how just-in-time debugging works, is that when you see one of these pop up, if you were to choose to debug the program, then the debugger will come up, and then you're essentially now debugging that program at this point in time. So from a software development standpoint, you can also you can have your own unhandled exception filter if you want to have your program be able to fail gracefully, essentially. I've also seen this used to detect debuggers by essentially intentionally triggering an exception, and if the unhandled exception filter is invoked or called that the programmer wrote, well, they can set a flag indicating that it actually was handled by them. If it isn't ever invoked, which would occur if a debugger is present, then that's one very simple, also easily defeatable way of detecting whether or not somebody's debugging the program. And that wraps up part 2 for our lecture. And as always, if you have any questions or follow-up about any of the material, feel free to shoot us an email. Thanks a lot.